Okay, so this will be the video review of the problems in the review packet in case you need that to study for the vector test. So problem 1 here, we're given five different vectors. You can see that two of them look like they're in 2 dimensions, u, v, and m, because there's just 2 components, and p and q, those are 3-dimensional vectors. And let's just remind ourselves what this means. Like, if I have the x, this is saying that the x component of this vector is 5. So the way to think about that is in a Cartesian plane. If I go 5 over 1, 2, 3, 4, 5, that would be the number in the x direction, and I'm going to the right because it's a positive 5. And I go up 8 little unit vectors, and the actual vector itself is the arrow connecting those two. So it would be 5 across, 8 up, and that would be what vector u actually looks like. And I chose purposely here not to start it at the origin, just to reinforce the fact that vectors can really start anywhere. They're free floating, and as long as it's pointing in this direction in an orientation that's 5 across and 8 up, that's how that vector, that's how to specify that vector. So the first question here asks me to find, this is scalar multiplication, so 2v, which means take vector v and stretch it by a factor of 2. Here we're going to take vector m and stretch it by a factor of 3, and then do vector subtraction, which I'd like to encourage you to think as adding the opposite. If I do a, this is a and b, I'm just showing the general idea. A plus b would be putting these things head to tail, a, b, and then connecting them from the starting point of a to here. So that would be a plus b is what that, geometrically that's what a plus b would be. And to do subtraction, we're going to add the opposite. So the first thing we would do is start with a, and then since we're going to add the opposite of b, we need to turn it around. Still put it head to tail though, because we're going to be adding negative b. So now when I add vectors, I starting point of one to the ending point of the other. Do this one in green. Draw that one. That vector there is a minus b. So that's sort of visually what we're doing here. But since these are in component form, it's relatively straightforward to do this problem. 2 times the vector v, if I just do scalar multiplication, 2 times, I'm going to go ahead and write this one is 3, negative 2. Remember, there's 2 different forms, standard unit vector form and component form. This would be easier to see here, 2, negative 2. And then we're going to subtract the vector m stretched by a factor of 3. And then when you scalar multiply by components, all I'm going to do is distribute that scalar to the 2 components. So 2 times 3 is 6, 2 times negative 2 is negative 4. Here we're going to distribute this 3 to these components. So 3 times negative 4 is negative 12. 3 times 6 is 18. Now when we subtract vectors that are in component form, we're just going to go ahead and subtract corresponding components. So here we're going to get 6 minus a negative 12 as the x component, and then when we subtract the corresponding y components, we're going to get negative 4 minus 18, and when I simplify this out, you get the vector 18, negative 22. Or you could write that as 18i minus 22j would be another acceptable way to write that. Okay, moving on. The dot product of u and m. Remember, the dot product is you take 2 vectors and you multiply them with a dot multiply them. Remember, we don't want to just say multiply vectors because it's ambiguous. We represent that with a dot. And then, see, u is 5, 8. M is negative 4, 6. Remember, the dot product tells us to what extent vectors are in the same direction. So the way we do that is we multiply the corresponding components 5 times negative 4, those are the red ones that I underlined here. The green ones is 8 times 6. We're going to go ahead and add those two quantities, and we're going to get negative 20 plus 48 equals positive 28. That's a positive dot product, so that's going to tell us that our vectors are going to have an angle between them that is acute, because there's at least some portion of the one vector that's in the same direction as the other. If I project onto that like I'm shining a light, you can see that this vector's got a little piece in the same direction as that, and that's why it's a positive number. Moving on, to find the angle between u and v, we also need, this is another place we need to use a dot product. So let's see, maybe I can try and sketch this realistically here. U looks like it's 5 over and 8 up, so U might look something like that. V is 3 over and 2 down. So 3 over, sorry, erase that. Oops. So 3 over and 2 down might look something kind of like that. So this is the kind of a, hopefully a semi-realistic picture of what we're looking for here. We're trying to find that angle. Remember, and then the dot, another way to think about the dot product is just the length of the one number times the length of the other number times the cosine of the angle between them, taking into account their relative direction. And this is the idea we're going to use to find the angle. So cosine of theta, I'm just going to rearrange this thing to be the dot product divided by the length of u divided by the length of v. And then we just have to go ahead and fill in the components here. U dot v, see u is 5, 8, dot product with v, which is 3, negative 2. And then the length of u, that's a Pythagorean theorem kind of thing, because it's up here you can see that's 5 over and 8 across, so we're just going to add the squares of the components and then take the square root, so that's the length of u. The length of v is the same idea, it's 3 squared plus negative 2 squared, and then we just have to really crunch this out here. 5 times 3 is 15, plus 8 times negative 2 is negative 16. This is going to be 25 plus 64. This is 9 plus 4. And this is getting hard to read here. So that's negative 1 at top, square root of 89, square root of 13, and that's going to equal cosine theta. And then from here, you would just do inverse cosine, and you just punch that into your calculator, and then you would get that theta is the cosine inverse of negative 1 over root 89, root 13, and you would get that theta equals 91.7 degrees. Slightly obtuse, which makes sense because you noticed here the dot product was a negative number, so we should have expected theta to be something obtuse, and that's really pretty close to 0, so it's not surprising that this thing is pretty close to a right angle. Okay, for this next problem, we want to find a vector of magnitude 2 in this same direction as m. So m is negative 4, 6, and if we want to just visualize what that is, it's 4 over, 6 up. So the vector we care about is this guy right here. This is m. And we want to find a vector that's in the same direction as m but has a length of 2. Well, really, this is just a shrink it down or expand it, scale it up kind of problem. So what we really need to find first is how long m is. So the magnitude of m is just applying the Pythagorean theorem again here, which is negative 4 squared plus 6 squared. And that would be square root of 16 plus 36, which would equal root 52. So if we left m alone, its length would be root 52, which is a little bit over 7. So we really just need to find, I don't know if they call this vector d. And we want it to have a length of 2. Well, d is just going to be, the scale factor is 2 divided by root 52. Basically I divide by square root of 52 to get it down to like a length of 1, and then I multiply it by 2. And then I just multiply it by my vector m, because that's still in the same direction. So this is really, all I'm doing here is finding this particular scale factor to make this problem work. And then if I go ahead and you could leave the answer like that, or if I went ahead and distributed that, it would be 2 root 52 times negative 4, comma, 2 root 52 times 6. Or any other variant. I think the answer key actually has the 2 factored out, which is fine. But any of these would be fine. This is okay. This is okay. I think then the answer key actually had this 2 comes out of it, and it would be negative 4 root 52 over 6 root 52. And you could do radical simplification if you wanted to as well. So that's the idea of those. You just take m and shrink it down by some factor. So this next problem is just a straightforward find the cross product. And if we recall that the cross product is this vector that's perpendicular to my other 2 vectors. So this is p and this is q. The cross product's either coming out of the page or going back into the page. P cross q. So the way to do this is, that's why we learned the determinant formula. So that's the approach we're going to use here. You create a determinant. The ijk vectors go across the top. We're going to put the first vector listed here. Order is important with cross product. So that's what's the components of the p vector are going to go there. The components of the q vector are going to go there. And then it's a straightforward application of the determinant. I'm going to expand across the top. So that's where the I, and remember we use the checkerboard pattern when you expand a determinant. It's plus, negative, plus, negative, plus, negative, plus, negative, plus. And so since we're expanding across the top here, we have to do positive I, negative j, positive k. And then you do the cover-up method, where if I'm expanding the I term, I cover up this column and this row, and I'm left with the negative 7, 3, 0, 2, 2 by 2 determinant right here. And the same thing, etc., etc. And then I'm going to assume you remember how to compute a 2 by 2 determinant, but it's essentially the product of this diagonal minus the product of that diagonal. So I'll just do this one as an example. It would be negative 7 times 2, which is this diagonal, minus 3 times 0, which is the product of that diagonal. And that's negative 14, and that's why that number is showing up there. And the relationship to vector p and q, like any cross product, is that it's in fact perpendicular to both, kind of like I tried to draw it poorly in this sketch over here. Hopefully f is a pretty straightforward idea. When we did parallel vectors, the idea was that if I took any given vector, call it vector d, any vector that's parallel to d is going to be just some scalar multiple of it, which means I'm just going to stretch it or shrink it to be a multiple of that. So like this vector could never be a scalar multiple of d because they're in different directions, whereas this one, if I just said, hey, is this one parallel, I could tell because I can see that it's in the same direction, and if I can shrink it down by some scale factor to be exactly d, then I know they're parallel. So that's the idea behind this one. If q is just this vector negative 4, 0, 2, I can just, this is asking you to find any vector, so I'm just going to pick some random scalar, called 2. And then so 2 times negative 4, 0, 2 would be negative 8, 0, 4. And that one would be parallel, or you could really pick any other scalar multiple that you want, even if it was a negative scalar, it would still be parallel. Parallel vectors can either be in the same direction or in opposite directions, and they're still considered parallel. So for this final question of problem 1, we're asked to find the angle between vector p, listed here, and the positive z-axis. So if we think about that in our 3D sketching, this is the z-axis right here. So we want to find the angle of p, which I'm not even going to try and sketch here, and that axis. So the trick, or not really trick, but the idea here is that anytime we're thinking about the angle between vectors, the dot product is what should come to mind. And so we want to think about the dot product of two vectors. And the hint here tells us we want to find a vector that points in the same direction as the positive z-axis. Well, let's just pick the vector k. Right? We know the vector k is pointing straight up the z-axis, and its length is 1, and that might make our problem easy to do here. So again, the dot product of two vectors is going to be the length of the vectors times the cosine of the angle between them. Cosine of theta would be the dot product over the product of their lengths. And so the dot product here is going to be, see, 1, -7, 3, dot 0, 0, 1. And then the length, now we have to think about the 3D Pythagorean theorem here. For p, it's going to be 1 squared plus -7 squared plus 3 squared. That's the length of p. And then the length of the unit vector here is just going to be 1. We need to apply the 3D Pythagorean theorem. And then the dot product in the numerator here, 1 times 0 is 0, plus -7 times 0 is 0. 3 times 1 is all we're left with on the top. And then on the bottom here, it's going to be the square root of 49 plus 1 is 50. Square root of 59 is going to be cosine of theta. And then you just punch that into your calculator to do the cosine inverse of 3 over root 59. Should give me theta, which should be 67.0 degrees to the nearest tenth.